Hello folks and welcome to ECMath. Today we are going to look at section 4.2. This is the second video in section 4.2. And in this video we're going to look at fundamental trig identities. A lot of people don't understand what I mean when I say identity. So I want to create a separation between the idea of an equation and the idea of an identity. So first, equations, and these are things we've seen before. An equation is a statement that is only true for some values of x, like 2x equals 4 is not true for all x. And what we do with equations, usually, not always, but usually, is we solve them to find the values of x that make them true. For this one, I could divide both sides by 2 and get the value x equals 2. And we call that the solution, because that is the value that makes the equation true. But if I said x equals 3, and I would do 2 times 3, equals 4, that's not true. So this is false, even. Whoa. So an equation is not true for every x. You can't just plug random numbers in and expect it to be true. But on the other hand, an identity in math is a statement that will always be true, no matter what variables you use. Before we do trig identities, let's just look at an identity you probably use like almost every day in math class. The identity is quantity a plus b to the second power is equal to a squared plus 2ab plus b squared. Often you just use that as a factoring pattern. Maybe you're factoring one direction. Well, if you're factoring, you're taking something that looks like this and rewriting it in a different form. But did it matter what a and b were, right? Sometimes it's x, sometimes it's 5, who knows? And that's what an identity is it's something that it's a structure that holds true for like all values. So instead of solving identities, we can prove that they are true. Sometimes that's called verifying them. You might prove that this identity is true by using the distributive property and confirming that it equals the expanded version. You might also prove that identities are true by constructing a diagram. This is a diagram of that same identity that uses an area model to justify why that expansion is valid. And then once we have proved an identity, we can use it in other circumstances. So if I'm doing x plus 3 squared, instead of writing out x plus 3 times x plus 3 and doing all the terms, I can just identify the structure that that's a plus b squared. And so x plus 3 squared must be x squared plus 2 times x times 3 plus 3 squared. And you can simplify that now to x squared plus 6x plus 9. So that's just an example of an algebraic identity that we use pretty much every day in math. Sometimes another word for identities might be patterns or formulas. I think technically the Pythagorean theorem is an identity, as is the quadratic formula, because it's true for almost, I guess, all values of a, b, and c. So identities are studies of relationships between quantities that are always true. Trigonometry is the study of the relationships between triangles and circles. So it makes sense that there would be a lot of true identities in this relationship between triangles and circles. I'm going to show you an animation that I did not make, so full credit to the author. I'll post a link to this site in the video notes, as long as it's still up. And this is like what I mean by triangles and circles, right? We have a point moving around a circle, angles from 0 to 360 or 0 to 2 pi in radians, and we have these values sine, cosine, and tangent that correspond with like different lengths in different parts of the circle. And we've looked at some of these definitions already. Sine is y, cosine is x. Let me come around here and pause this. But it turns out that a lot of the trig functions can sort of also be thought of as living on this circle. And so we're looking at these relationships, geometric relationships often, between trig quantities. And there's a bunch of identities that relate them. And these identities, of course, don't depend on any values, so we're generally going to use just the variable x. You could also write theta here to remind you that it's an angle, but x is fine. And the idea is that these are true for all x or theta, right? It doesn't matter what x is. These are always true relationships. So the first bank of true identity relationships are called the reciprocal identities. And these are the identities that talk about which functions are related to which ones through the reciprocal idea of being reciprocals of each other. So we already know that secant of x is 1 over the cosine of x. Right? That was just how we initially defined secant. And so cosine of x we will also write as 1 over the secant of x. We know that the cosecant of x is 1 over the sine of x. And reciprocally, the sine of x is 1 over the cosecant of x. And the cotangent of x is 1 over the tangent of x. And the tangent of x is 1 over the cotangent of x. So these two identities are reciprocals of each other. If you have one, you can replace it with 1 over with its reciprocal. And another identity is that about tangent. We know that tangent is 1 over cotangent, but sometimes it's actually more useful to think about tangent as sine of x divided by cosine of x. Now let's hold on for a second. Why would that be true? Well, if you remember, on the unit circle, we had a triangle. We're on the unit circle, so the hypotenuse is 1. There's our y. There's our x. And we knew that y is equal to the sine of x. Sine of theta, because I already have an x. And x is equal to the cosine of theta. But what's tangent? Tangent is y over x, which means that tangent is sine over cosine. And that's basically a proof of this identity. You could be a little more formal if you write it out, but that's a proof of this identity. Tangent is sine over cosine because it's y over x on the circle. And kind of combining two ideas, if we know tangent is sine over cosine, and cotangent is 1 over tangent, then it also must be true that cotangent is cosine over sine. So that's the tangent identity for cotangent. It's cosine over sine. And a cool thing just happened. Is we use two identities to prove a third one. They're very simple. But that's like often how identities are used, is you start with this base of fundamental identities, and you start creating new relationships or new things. Here's an example of what I mean by that. And this is a type of problem that you're going to see a whole lot later on in Chapter 5, but even here in Chapter 4, this kind of stuff, being able to manipulate trig equations, very useful. So, say I wanted to simplify 2 cosecant of x over cotangent of x. Ew, gross, like all those co-functions? All right, so here's what we'll do. We're actually going to make a complex fraction and kind of take these apart. So cosecant, I'm just looking over here, is 1 over sine. So this would simplify to 2 over sine of x. And cotangent, looking over here, is cosine over sine. So I've actually made a complex fraction, which seems gross, but what's nice now is that everything's kind of in terms of the same expressions, cosine and sine. So we can do another step. This is the same as 2 over sine x times the reciprocal of the bottom, right? Keep change, flip, you take the reciprocal of the bottom, and this is then times sine x over cosine x. Well, sine x times sine x, that'll reduce out, and you get 2 over cosine x. But that's still kind of in a fraction, so we could think about this maybe as 2 times 1 over cosine x. And we could think about that as 2 secant x. So to fully simplify the expression 2 cosecant x cotangent x over cotangent x, that actually fully simplifies to 2 secant x, going through this kind of little chain. It's nothing but fractions, But you're going through this little chain of reasoning until you get that complicated expression down to a single expression. And actually, technically, this is a new identity now. That 2 cosecant x, no matter what x is, over the cotangent of x would always equal 2 times the secant of x. Now, is this an identity that you should memorize and use every day? No, but it is actually a new identity. And that's what we use these fundamental identities for, is proving new ones. Now we're going to talk about what is probably the most important identity in all of trigonometry. Before I write it, let me share with you why this identity is true. So, imagine that we're in a quadrant, we have an angle, we've rotated around. Just for simplicity, I'm going to draw this in quadrant 1, but it could be in any quadrant. We have this height, y, which is equivalent to the sine of theta. And we have this adjacent side, which we say x is the cosine of theta. And we know that the hypotenuse here in the unit circle is 1. And that's important. We're going to let the hypotenuse be 1 on the unit circle. Then, by the Pythagorean theorem, which says that a squared plus b squared has to equal c squared, it must be true that cosine of theta, whole thing squared, plus sine of theta, whole thing squared, must equal 1 squared. And that's what we call the Pythagorean identity. What is it? It's just a formulation of the Pythagorean theorem. Usually we write it slightly differently, though. We write it as cosine squared theta plus sine squared theta equals 1. So this is like a very weird notational thing, but when you have an exponent up there that is actually an exponent, cosine squared, just know that that means cosine theta whole thing squared. The reason we put the 2 here instead of there is that then it doesn't look like you're squaring the angle. If you put the 2 at the end and then got sloppy in some other ways, it might look like you were squaring the angle, which is not something you ever really want to do. So we write it as cosine squared up there. And this is always true. This is just a relationship that's always true whenever you have sines and cosines and they're squared. They're always going to simplify out to 1. So let's use this in another example to simplify some expressions. So I want to simplify 1 minus cosine squared x over cosine squared x. Now, one thing that you can do with identities that's pretty neat is rearrange them and keep them true. So this is always true, right? Cosine squared plus sine squared must always equal 1. Well, if I take away cosine squared from both sides, then it would be true also that sine squared is equal 1 minus cosine squared. And if I take away cosine squared from both sides, it would be true that cosine squared is equal to 1 minus sine squared. So we have one main identity, but we actually kind of get 3 for the price of 1. Ah, what a great deal, right? And now I see some things that could directly substitute in this simplification. So I have 1 minus, I'm actually just rewriting it, cosine squared x over cosine squared x. I'm using x and theta interchangeably here. It means the same thing. So like it's okay to switch around your variables a little bit. Well, 1 minus cosine squared x is, where is it? Right here. That's equivalent to sine squared x. So I'm going to directly substitute based on that identity in green. Actually, I'm going to do that in green. Directly substitute sine squared x for the entire expression 1 minus cosine squared x. And I'll rewrite the bottom. And then a cool thing has happened also. We have sine squared over cosine squared, which if you think about it is like sine of x over cosine of x whole thing squared. Well, sine over cosine, that's tangent. So we have tangent of x whole thing squared. So we will actually say that this is equal to tangent squared of x. So we've just now proven a new identity, which is that 1 minus cosine squared x over cosine squared x is equal to tangent squared x. Again, is this a useful identity that you should, memorize? No. But it is a true fact that'd be true for all x around. And actually, just to highlight a cool connection, which is that the reciprocal identities also work with the functions squared. So like 1 over sine squared x is the same as cosecant squared x, for example. And not everyone immediately recognizes that, but it is actually true because you're just squaring the thing, and then like the power, it's the rules of exponents guarantee that that's true. One last observation on this problem is just when you're working with trig identities, it can be unclear where to start sometimes. So, for example, you may have said, what if I start with substituting something for cosine squared? There's nothing that says that's algebraically illegal, but I think if you substitute something in there, it actually becomes more complicated. So it's more of like an experience thing, that figuring out what you want to substitute to simplify things, what will make things more complicated. The more of these you do, the better you're going to be at it. If you find yourself chasing yourself in a circle, don't be afraid to just cross out all your work and start again fresh with a new strategy. It's always okay to start again. So one of the themes of this identities page has been rearranging old identities to make new identities. And it turns out that this key identity, cosine squared plus sine squared equals 1, can be rearranged in two really, really useful ways. And they're also called Pythagorean identities. And I want to share those with you now as well. So in this first box, I'm going to start by writing cosine squared theta plus sine squared theta equals 1. And then I'm going to divide both sides by sine squared theta. If I do that, some interesting stuff happens. First, cosine over sine is cotangent. So cosine squared over sine squared would be cotangent squared. Sine squared over sine squared is just 1, and 1 over sine squared is cosecant squared. So this is another Pythagorean identity that you can use that relates cotangent squared to cosecant squared. So if you had a problem, similar to this one, but it had cotangents and cosecants in it, you would probably use the identity that's I've just put a star on. And so that's another one, not quite as critical to have memorized as the first, but really useful. And you should have it memorized. You should learn that identity because it will always be useful to you. And similarly, if I start with the same identity, cosine squared theta plus sine squared theta equals 1, and divide that by cosine squared, then we get the identity that says 1 plus sine squared over cosine squared is tangent squared, and 1 over cosine is secant squared. So we get the identity 1 plus tangent squared theta is equal to secant squared theta. So if I was doing a problem like the one above, but instead of sines and cosines, I had tangents and secants, I would look to substitute using this red identity. Just to keep this video short, I'm not going to do an example that uses these, but you'll see it come up in the homework. Instead of converting to sines and cosines, it's almost always more efficient to actually just directly use one of those two identities. So make sure you have those down and make sure you start trying to learn them. The next group of identities we're looking at are called the even and odd identities. And just to remember from chapter 1, even in terms of functions, not numbers, means that f of x is equal to f of negative x. And that was a statement about symmetry. So that if we had x and negative x, then a function with even symmetry would have the same values for all x and negative x. So maybe here's a function with even symmetry as a vertical line of reflection. And odd functions mean f of negative x is the opposite of f of x. So if I had some x and some negative x, right, equal and opposite, then we'd have a function that does this. Oh, actually, I want to do it like this. I might have a function that does this, but then at its opposite point, it has the opposite value. And so that was kind of rotational symmetry around the origin. That's what even and odd meant for functions. Now, when we talk about trig, we are not talking about the graphs of trigs yet. We're actually talking about the unit circle. So when we talk about positive and negative, we're actually talking about angles going clockwise or counterclockwise. So for example, here's our coordinate system. Here's our initial side of an angle. And that angle could open clockwise. We'll call that the positive direction. Or counterclockwise, the negative direction. And assume that these are the same theta. So we'll call that, negative theta, and we'll call this positive theta. And we want to think about what trig values would be the same with positive and negative thetas. So here are the identities, and then we're going to refer back to this picture to justify why they're true. The first identity is that cosine is even. That is, cosine of negative x, I'm going to write it as theta, although it's often written with x, is equal to cosine of theta. That is, if you have a negative angle as the input, it will have the same cosine value as a positive angle with the same size. Why is that true? Well, think about our positive and negative angles with the same size over here. Cosine's the x-coordinate, and those positive and negative angles actually have the same x-coordinate. So they're going to have the same cosine values. Because they're both pointing either both left or both right. So cosine is actually an even function. And I'm going to also say, and its reciprocal, secant of theta, is even as well. So that's the first even-odd identity, is that cosine is even. The second even-odd identity is that sine is odd. What that means is that sine of negative theta, the sine of a negative angle, is the opposite of the sine of an equal positive angle. Now, why would that be true? Well, let's look at the picture again. Sine is the y-coordinate, so the sine of this green angle would be positive because it's the y-coordinate, it's going up. But this negative angle would have the opposite sine value because it's going down, even though it's the same angle, so the length of that blue scribble would be the same. So sine is an odd function because the y, when you turn clockwise, initially goes up, but when you turn, I said that backwards, when you turn counterclockwise, it goes up. When you turn clockwise, the y goes down. So sine is an odd function. And conveniently, so is its reciprocal, cosecant. And actually also, tangent is odd. And if tangent is odd, then cotangent is also odd. So actually, most of the trig functions are odd, and they have this property here. I'm not going to rewrite it just for space reasons, but cosine and secant are actually even functions. Okay, so how do I use this? Well, this one's kind of weird to use in a problem. It actually is more useful when thinking about graphs. But say I want to compute sine of negative 2 pi over 3 without drawing a negative angle, because I don't know, my negative brain is broken today. Well, since sine is odd, I know that sine of negative 2 pi over 3 by this identity would be the opposite of the sine of 2 pi over 3. That's what the identity tells me. Well, okay, I know what 2 pi over 3 is. That's this angle in this quadrant. So that height would be root 3 over 2 with a hypotenuse of 1. So then I know that the opposite of that would be the opposite of root 3 over 2, which should be the sine of negative 2 pi over 3. So there's a good way to use even-odd identities is to just simplify your angle calculations if you don't feel like dealing with negative angles. So for the next bank of identities, I want to close by looking at the picture we started today by looking at and noticing that all of these identities and relationships about trig come from a circle. And as the point moves around the circle, notice that everything just repeats over and over and over again. Sine, cosine, tangent functions are all about repetition. And so those functions are called periodic functions. They're functions that repeat after a specified interval. Let's go ahead and define that. So a periodic function is a function that repeats on regular intervals. And what that interval, the interval that of repetition, is called the period. Here is a picture of a periodic function that I just looked up. And interestingly, this is not a trig function. So you don't have to be a trig function to be a periodic function. A lot of people think you do. What I like about this picture is that it shows that the period is the exact time it takes to repeat. So the period is from those two valleys to the valleys. And usually with a periodic function, you can measure the period from any two of the same point and you'll get the same measure because it has to repeat on regular intervals for its whole cycle. So trig functions, because they come from circles, are almost guaranteed to be periodic. They are going to repeat on regular intervals. And so we have some identities that talk about that. So let's talk about sine and cosine first. And tangent and cotangent are like a little bit of their own special bird here. But sine and cosine start at 0 and rotate through the quadrants, right? You know, we're looking at an angle as it rotates. The angles in all the different quadrants, getting different values, positive, negative, until we get all the way back to 2 pi radians. And then if we go around again, eventually we'll just get the same values in the same cycle. So that means that the period of sine and cosine is just one full trip around the circle. So we'll say the period of sine, cosine, I'm just going to write it as sin, cosine, and their reciprocals, so secant and cosecant, is 2 pi. And we'll write that as an identity by saying that sine of theta is equal to the sine of theta plus 2 pi k. What does that mean? It just means that you can go around the circle k times and get the same values. That's what we mean by plus 2 pi k. You can even write plus or minus because you can go backwards around the circle and get the same values. Every time you go a full trip around, you'll get back to the same point. And we can write the same for cosine, so we'd write that cosine of theta is equal to cosine of theta plus 2 pi k as well. And we could write the same for secant and cosecant. Let's do an example with that really quick. So say that I had to find sine of pi over 2 plus 24 pi. Well, I think the naive way to approach it would be to figure out what that is as a radian and then compute that I don't know. But instead I'm just going to think about 24 pi is 12 times 2 pi. So this whole angle is just pi over 2 plus 12 extra trips around. So if I want to do sine of pi over 2 plus 24 pi by the identity that I wrote above, that is equal to just the sine of pi over 2. And I still have to compute sine of pi over 2. So pi over 2 is up here, 90 degrees. It has coordinates 0, 1. Sine of theta is equal to y. So the sine of pi over 2 is the y coordinate, which is 1. But so sine of pi over 2 plus 24 pi, same as sine of pi over 2, which is 1. A lot of times when you need to use a periodic identity, it's pretty clear because you never really get a thing that looks like that in your argument unless you are literally doing exactly this. It's not like something that comes up in different weird contexts. It's pretty clear when you're supposed to use these identities. Let's talk about tangent. Tangent's a little goofy. It actually turns out that the period of tangent is pi. And we'll say and cotangent. Not 2 pi. Why would that be true? Well, remember for tangent, let me zoom in a little better. Remember that for tangent of x, in the first quadrant, tangent was positive, and then the second quadrant, tangent was negative, and in the third quadrant, tangent was positive, and in the fourth quadrant, tangent was negative. Well, so then as you're cycling around the quadrants, you do positive, negative, then you get to pi here, and you're just kind of repeating that positive, negative cycle. So the tangent sort of cycle of values is plus, minus, plus, minus, plus, minus, plus, minus, every pi radians. So tangent actually repeats faster than cosine and sine. So for tangent and cotangent, it has a slightly different periodic identity. We write that the tangent of theta is equal to the tangent of theta plus pi k. That is, we only need to go half trip around the circle to get back to the same value of tangent that we had before. And cotangent of theta is cotangent of theta plus just pi k. This is going to be the most important in like a month or two when we start solving equations that involve tangent and we're looking for all solutions. Tangent equations have more solutions than sine and cosine equations because tangent cycles faster through its values. For us, for now, let's just use it to do this one problem. So we're doing tangent of 3 pi over 4 plus 17 pi. Well, by this identity, that's just 3 pi over 4 plus, or I should say this angle is just 3 pi over 4 plus, sorry about that, it's 3 pi over 4 plus, 17 half trips around the circle. But the period is 1/2 trip. So by the identity, tangent 3 pi over 4 plus 17 pi is equal to tangent of 3 pi over 4. That's just what we have. Then we still have to evaluate this. So 3 pi over 4 is over here in this quadrant. Oh, there it is. Tangent is opposite over adjacent. And in this quadrant, we'd have a -1 and a +1. So the tangent is opposite 1 over adjacent -1, which simplifies to -1. So that's how we might use that identity. And that's it, folks. Trig identities are a really deep topic that are needed for solving some of the hardest trig problems. Right now, we're just dipping our little toes in and getting used to some of those fundamental identities. By the time this section is over, this chapter is over, I should say, you will need to have all of those identities memorized. It's not urgent. You don't have to do it right away. But by the time we get to chapter 5, you're going to be using those basically every day, and it's important that you know them. So you may want to start studying them now. I hope this has been informative. Let me know what questions you have, and as always, I'll see you all next time.